First off, any questions from homework stuff? Yeah.
On 3.2, number 40, it says that it's mutually exclusive, so could you do the E given F? Or, like, I just didn't understand.
I love it. All right, so a couple things. If I tell you that E and F, they're events like A and B. A and B are the ones we build our formulas for, but then they could be anything. So capital letters for probability, like normally have lowercase x and lowercase y for variables in algebra. Capital letters in probability stand for events. So E could be the event that you buy a carrot cake, and F could be the event that you forgot to bring your stupid plastic bag with you, so you have to carry all your groceries out to your car or buy another one. You guys with me? Jesus, this happened to Jeff a lot. Want bags? Why not? My house is not completely full of bags yet. I got some. If I tell you that E and F are mutually exclusive, who remembers what that implies or that means, that tells me about them?
Probability happening 0.
Yeah, probability that they happen together. If they're mutually exclusive, the probability they happen together is 0. That's the whole idea, right? They can't happen, as I say, they mutually exclude each other. Right? So I like one example I like is, if I pick up, it's a bit old. If I pick up a puppy, what's the probability that I have a tablespoon that I just picked? No, it's a puppy. It's a 0. The tablespoons and puppies. They haven't made that weird ass cartoon yet. Tablespoon puppy. No. So the probability E and F is 0. Now, is that coming from next door? Oh crap! I always hate competing against videos. You're going to have English statements like this that you must translate into a probability fact, because then you have to use them in formulas, right? So this information isn't something just to gloss over. This is going to help you actually answer the dang thing. So now, in this problem, they ask you, where to go? Oh, find the probability E given addition. Probability of E is 0.4. The probability of F is 0.5. And recall, what's probably of A given B? Who knows that formula? Or can look it up real quick because I don't make you memorize them. Probably A and B over. Good. The given's got to go on the bottom. I love it because students sometimes forget the idea behind a formula, but the idea is if I give you information, it's going to knock down what the total possibilities are. And the bottom is the total number of things it could be. So if I tell you that it's men, then the bottom's got to be probably is a dude. I'm going to throw all the women out. It's got to be a dude. You with me? Okay. So now they ask you, what's probably E given F? Yep. Well, what's the formula for that? Probably E given F. What's the formula? Probably E and F over the probability of F. Well, what's probably E and F? Yes. See, and this is what people will skip over. Now, the person who asked the question didn't skip this over. She asked it perfectly. But you'll skip this over. You'll try to throw this in here somehow. Right? But this is important. They told me it's mutually exclusive. I know this is 0. This is going to be 0 over. It doesn't really matter. But just to complete it. What's 0 divided by 0.5? 0. Like, no chance. And let me go a step further with my puppy and tablespoon example, right? Just go with me for a minute. Let's say in a room, there's an equal number of puppies and tablespoons sitting out there, right? I get blindfolded. This is the weirdest day of my life. I walk in, and I reach down, I pick up something. At this point, I should know, but let's say all the nerve endings in this hand don't work, right?
Is it fuzzy or is it cold?
It's like Aunt Mize Johnson. I also have no feeling. I don't know what it is. So what's the probability it's a puppy? Remember, equal amounts of puppies and tablespoons, so it's probably just picked up a puppy. 50%, right? I take my blindfold off. And I see that it's a tablespoon. So given that it's a tablespoon, what's the probability that I've got a puppy in my hand? Frickin' 0. Right? So the given will always go to 0 when the two things are mutual. Once it's one of them, how could it also be the other one? Given that it's a tablespoon, what's the probability it's a puppy? Oh, shit. Ain't got no chance. You guys get that? That's really the idea behind the math. But the math is pretty straightforward as long as you remember that this means this. Yes?
What did you say, or what was the end of the sentence? You said given will always be 0 when what?
Okay, all right, well. So a given will always be 0 when the two events are mutually exclusive. But, don't turn that into necessarily something to memorize. See why that makes sense. A real quick word about math. The people that aren't very good at math are the people that think that math is all memorization. Oh my God. You're never going to make it very far. Your brain's going to get full. I ain't got that much room in my brain, right? Forget my mom's name. I have to make room for something. No. It's all about why does it make sense so I don't have to remember it. It just makes sense. Okay, I like it. Okay. Anything else from homework stuff? Yeah.
3.1.
You get 2 classes for the price of 1 today. If you can make out what they're saying. 86? 36. Oh, the one about the shelf holding 12 books? Okay. 8 are fiction and the rest are non-fiction. Each is a different book with a unique title. So this one is a little bit weird. So there's 12 books. 8 are fiction. And the rest are non-fiction. So amazing that'd be 4 non-fiction. Blah, blah, blah. The fiction books are numbered 1 to 8. The non-fiction books are numbered 1 to 4. Oh, number 7, my favorite book. What's the sample space? Okay, what the hell? This is one little detail I don't think I've talked about yet. I haven't really talked about the sample space yet. But all the sample space is just a collection of everything that could happen. All the individual outcomes that could happen. So, give me a way to identify the third book of the fiction sequence. F3. Right, sounds like a tornado. So what is the sample space going to be? Well, what could happen if I pick a book? What could happen? I could get F1. Or I could get F2. Or, all right, and then I could get N1. So if I roll a die, what's the sample space going to be? A normal die, not a Dungeons and Dragons kind of. Yeah, 1, 2, 3, 4, 5, 6. That's going to be the sample space because that's the 6 things that could happen if I roll a die. You guys kind of with me? So going with that die example real quick. So I roll a die. The sample space will be 1, 2, 3, 4, 5, 6. Now I could define an event. I could define event A. I can define it to be an even number. So an event is any collection of outcomes that you can define whatever way you want to. Right? So an event could be several different outcomes defined in a certain way. So in this case, an even number is defined like 2, 4, 6. Right? You guys with me? Or I could define B to be the number starts with the letter T. Right? I'm going to define an event any way I want to, but it's going to be some collection of things that are in the sample space. I like it. I like it. I like it. So that's the connection between events and the outcomes in the sample space. These are all blah, 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 individual outcomes. Doing something once, what could happen? It's just like this. Pick a book. What could happen? Well, I could get the first fiction book. Or the second fiction book. Or the 4, not too bad. I like it. Okay, I like this. I'm filling in the gaps through homework questions. Love it. Anything else from homework stuff? Was that cool? Was that? Anything else from homework? Okay. All right. So let me go back. Let's make sure we hit everything. Have we talked? We haven't talked about independent yet. I don't think. So we're going to do a card example just because. How many suits are there in a deck of cards, in a regular deck of cards? So taking the Joker's out, 4 suits. I love the reaction. Oh, God. What are the suits, real quick?
Spades, hearts, clubs,
Spades,
diamonds, hearts,
clubs,
diamonds,
hearts. Sounds like Lucky Charms.
hearts, stars, horseshoes.
How many are each of these? 13. Because there's how many total cards? 52. Why did I do this like this? These 26 cards are something special. Why are these 26 cards? What's the similarity between spades and clubs? They're black. And then these cards are 26 black, 26 red. Do you see how cards are just like, make a probability problem out of us? They just desperately want that to happen. Then you got the one eye Jackson on him. I'm not going to bring it there.
Oh my gosh.
Well, don't worry. I'm not going to bring it there. All right.
You almost did.
Now, I wish I remembered. Get these giant cards. Let's say I pick a card out of a deck of cards, and you're going to put some money down on what that card is. Right? So, let's say that you think, just to kind of guide this discussion, let's see. So I pick one card. And I'm not going to make it so much that you have to guess exactly which card, like the king of clubs. But let's just say you think it's a king. You with me so far? I picked a card, and you're like, I think it's a king. What's the probability that the card I picked is a king?
4.
Yeah, there's 4 kings, 1 in each suit. Right? Each of these go from ace, well, let's say ace is low, 2, 3, up to 10, and then jack, queen, king. So there's 4 kings, 4 queens, the 2 black ones and the 2 red ones. You guys with me so far? Okay. So the probability is a king, and this is the basic idea of probability. There's 52 things it could be, and out of those 52 things, 4 match what I'm looking for. Please, dear God, nobody make the mistake of saying the probability is 1/4. I think we talked about that before. That's somebody thinking, I want 1 king and there's 4 of them. No, you aren't somehow magically only picking from the 4. No, it could be any of the 52 cards. And there are 4 chances to get what you want. Now, somebody help me out. What is that as a percentage? What's 1 out of 13? What is it as a percentage? Oh, you were like, ask me to reduce it. Come on. So like about 7.7%. Okay. So are those good odds? Is that a good chance that you're going to make money? No. So it's probably a good return, but it's not a good bet. Right? So it depends on how much of a gambler you are. And I'm going to let you ask one question. And then you can determine whether or not you want to put some money down on this. I'm not going to let you change your bet, but I am going to let you determine how much money you want to put down. So a question you could ask is it a king? But, you know. What could you ask that would actually improve the chances it's a king, possibly? I mean, let me see. What if you ask, somebody think about a question. I mean, what could you ask about the card? Is it a... You could ask, is it black? Is it red? Is it a club? Is it... So let's say you want to know, is it a club? And I say, yes, it is. It is a club. Did that change your probability of making money at all? No. Let's see. So really what I'm asking is, didn't I give you information? I say, yes, it is a club. So what information? I just told you it is a club, right? Given that it's a club, what's the probability it's a king? Well, how many clubs are there? 13. There's 13 clubs. Not the kind to go into in so there's 13 clubs. Out of those 13 clubs, how many are king? One. Which is the same thing, of course. If you put that in the calculator, you get a point on center. You haven't improved the chances at all that it's going to be a king, right? So what's kind of a better question again? So this, would you say that king and club, those two events, are they dependent on each other? When club, I told you that it's a club that I picked. Did the probability that it's a king give a shit about that? No, it stayed exactly the same. So what do you think we should call that? Does it sound like we should call that dependent or independent? Freaking independent. It makes sense, right? I told you that the club happened, and the king, the probability didn't care. That is independent. So if the given probability does not change from what it was before, that's independent. And don't worry, I'm going to write this up very nice and formulaic as a test for independence in a minute. So what about if I tell you, if you ask me, is it a face card? And I say, yes, it's a face card. So instead of asking, is it a club, we ask, is it a face card? Now, how many face cards are there in a deck? Yeah, there's 3, Jack, Queen, King. They have faces looking at you. And for each, so 3 times 4, you got 12 face cards. So it's a probability it's a king given that it's a face card. Well, how many face cards are there? 12. How many of those face cards are kings? 4 of them. So now you got a 1/3 chance. You got a 33.3 forever % chance. You just, multiplied your probability by about a little more than 4. 4 times as likely to make money on this. You guys? So are these independent of each other? No. Because if I tell you that it's a face card, does that change the probability it's a king? Yeah, it used to be 7.7% roughly, and now it's 33.3%. So let me formalize this idea of independence. Okay. Here we go. I'm going to formalize this. Just want to give you guys, everybody got that, what they want from this? Okay. More than you wanted, probably. So here we go. If I ever ask you, are these two things independent? Are A and B independent? Here's how to tell. You can't just answer this with a paragraph. Well, clubs can happen without the king. No, it's got to be a mathematical proof, right? And people hear the word dependent and they think, like the other day, is driving a Harley Davidson motorcycle and being a man, are those probabilities independent? No. Probably you're a dude if you ride a Harley Davidson motorcycle. It's going to be higher, given that you ride that motorcycle, right? So people think, well, no, you don't. If you ride a Harley, you don't have to be a man. So they're not dependent. No, that's the wrong idea. Do the probabilities change? Not can it only happen if the other one happens? That's not what that means. Will the probability of one thing change, knowing the other thing has happened? That's what it means. So are A and B independent if the probability of A is the same as the probability of A given B? So I tell you B happens and A doesn't care. Then they are independent. Otherwise, they would be dependent. So if I tell you something happened and the probability changes because of that information, please let that make sense that we call that a dependent situation. What's the probability of A? Well, if it doesn't equal this, then it depends on if this happened or not. That's Here, does probability A depend on if B happened or not, if this is true? No, doesn't give a shit if B happened or not, right? It's equal to this number, whatever it is, no matter what. So that's why we would call this independent. I like it. Maybe. So we got the idea of independence. So if they tell you A and B are independent, you can write this. You know this is true in the homework. If they tell you D and C are independent, then you know probably D given C equals probably a D. You know that's true. Just like the one we did earlier about mutually exclusive means they're equal to 0. When you AND them, you can write that down immediately if they say mutually exclusive. I like it. You guys are sort of with me? You're all looking this way? Okay. That's step number 1. All right. So the idea of independence, that's the idea of independence. There's also, what formulas have we created so far? I was trying to keep that one and then I just erased it. We got this one. Who remembers what this one was? Adam. Good.
But you don't
But
any similar same thing.
what's the adjustment we have to make?
Subtract them, the difference between
Subtract any that are both. If you count all the A's and the B's, but there are some A's that are also B's, you counted them twice. You better subtract them off once to make it fair. So minus probably the A and B. So notice, or, this is going to come up decently often in this class, or is basically add. I say basically because there's a little adjustment, but or means add, basically. And is going to mean something, basically, here in a minute. We're going to figure it out. What was probably A given B? We just had that up here a second ago.
A and B over B.
I like, right? Now here's what's interesting. Do you notice how I have a formula for A and B? I just have to write it. It's here. It's here. There's the probability of A and B. Can you solve for this? So on one level, this is going to be a little anticlimactic in a way. Just solve for it, and you get this formula that we don't even know what it really means yet. But let's get it first, and then we'll explore what the hell it means. So probability of A and B. How do I solve for it here? What do I have to do to solve for this? What do I have to get rid of? I want to get this by itself. So what do I have to get rid of? Yes. Yeah, exactly. Why is this not by itself? Because of this stupid shit. So how to get rid of this stupid shit? I do the opposite of what it's doing. It's good old basic algebra, right? Do the opposite of both sides. Multiply both sides by P of B. And you get probably of A and B equals probably of B times probably of A given B. So that's like a brand new equation. It's not brand new because we just built it off of one that we already knew. I'm going to write it again up here. I'll write it in a different way too. Probability of A and B is probably good job. I just approximate the word. Sounds that approximate the word on it. Probability of A and B equals probability of B times probability of A given B. Or probability of A times probability of B given A. So let's explore real quick in two different methods why it would be multiplication at all that and would mean multiplication, and then we'll get more specific about what the shit is this here for. You know, why is it a given there? We'll get more specific about that in a minute. So these are really silly examples. Don't overly analyze the first one. The first one I'm going to do is really silly, and the second one I'm going to do is related to the space shuttle blowing up. So it's not quite as silly. The first one is, let's say I want to join a fraternity, right? And they're going to haze me lightly, okay? I got to walk down this hallway to all these doors, and every fifth step I take, somebody opens the door and slaps me in this cheek. And every seventh step I take, somebody slaps me on this cheek, right? You guys with me? You guys understand? I don't care what you think about it. Just that's the reality. It's happening. Every fifth step, bam. Every seventh step, bam. Right? How often will I get hit on this cheek and this cheek? 5 steps, bam.
Twice every 7 steps.
7 steps, bam. I want to know, when will this happen? Right? Somebody will open the door from both sides and just attack me. Yes, right? Every 35th step. You with me? So probability I get hit on this cheek is 1 out of 5. The probability I get hit on this cheek is 1 out of 7. And what is 1 out of 5 times 1 out of 7? 1 out of 35. I love it. So this idea of multiplication sort of naturally happens. Don't overly analyze it because it breaks down a little bit with different numbers. But that's just my silly kind of example. Here's a more serious example. I don't know if you guys realize, at least the one that happened back in 86, I think it was. This is when Jeff was in English class. I remember this. I remember the class, and I was crying when I found out that it exploded. But it was because of these things called O-rings. So what an O-ring is basically is a valve to make sure the gas only goes one way, not the other. So let's say that, for the sake of simplicity, that we have these several O-rings down this pipe. Let's say just say 2, right? And each one has like a 1% chance of failing. Now, why would I put several of these O-rings in there in a row? So what's that word? You know what the word is? It starts with a C? Plan. You have to have a contingency plan. Sorry. What a way to get. It's the same reason you would put multiple locks on your door, right? In fact, the multiple locks, probably there's a few different types. You're like, okay, you can get this one open, but you better be able to get the other ones open or you ain't getting my house, right? You would hope to God that the probability that both of these fail, this one and this one, is not just adding these things together. Then why the shit would I do it? You put 2, and that was a 2% chance it's going to fail. Good job. No. So that doesn't make sense. And I don't know if you know this about numbers, but normally when you multiply 2 numbers, the answer gets bigger. But when you multiply 2 numbers that are between 0 and 1, which is where all probabilities live, the result is smaller, right? What's 0.5 times 0.5? A half times a half is a quarter. I like it. What's 1%? 0.01 times 0.01. If you like it even better, what's 100th times 100th? 1 over 100, 100. 1 10,000ths. It's being 0.0001. So then that's the probability that they will both fail, which is awesome, which is better, right? I'd probably put a few more in there just to be extra sure. Like if there was a crazy important test the next morning early, are you gonna? I always do this. Are you gonna have one alarm? You're gonna have at least 2 things. You're gonna have your phone and like an alarm clock or something, somebody else's phone, whatever, right? You guys with me? You guys understand? Why do you do that? So that the probability that neither one of them work is low, really low. The probability that you will wake up is high if you have more things in place. I like it. I like it. Okay, now, so the idea that you multiply for and hopefully makes a little more sense now. Okay. But why is it specifically that, and not just because it came from this equation? I want to see a better example. Jeff, come on, math boy. Let's do this. Let's go to your classic probability problem that I haven't done yet. I've been staying away from it sort of on purpose. Let's say we put 4 red poker chips and 3 blue poker chips and 7 green poker chips in a bag. Then you reach in. Let's do this 2 steps. First step is pick 1 poker chip. What's the probability that you get a blue poker chip?
3 out of 14.
Yeah, 3 out of 14. There's 14 total. And there's 3 chances out of those 14 to get a blue one. And you can make it into a decimal percentage, whatever they are. Right. All right, I can ask you some more questions, but who cares? Let's jump to the more interesting problem, the new problem. I want to pick 2 poker chips out now. And I have to be specific about how I want to do it. Pick 2 chips. Well, how many ways is there to pick 2 chips, really? I could pick a chip and then pick another chip. Do you notice how if I do that, I don't put this one back? What changes mathematically? The bottom and maybe the top. It depends on what I'm looking for, right? So let's do the first way, which is you take it out and then you drop it back in. And why is that kind of preferable sort of mathematically? Because then all the probabilities stay the same. They're all going to be out of 14 still. So pick 2 chips. With replacement is what it's called. With replacement means you put the first one back in before you pick again. What's the probability you get a red and then a green? So what's probably the first one is a red one? 4 out of 14. So that has a 4 out of 14 chance. And means multiply, right? You put that one back in, and now I want a green one after that. So it's probably the next one's a green one. 7 out of 14. I like these numbers because 28 out of 14 times 14 is 2 out of 14, 1 out of 7, which is like 14. No, Jeff. Is it 14? Yeah, it's like 14.7%. I think. Is that true?
1.2856.
Okay. I think 14 is not too bad for human. I like it. Is that? Do you guys see it? Sometimes it's better to actually not multiply the things out so that you can see how they cancel. All right. Doesn't matter. No, y'all got calculators. All right. Yeah. Of course, this is 1/2 of 4 is 2 is another way to look at it. But now, if I would have said red and then blue, the only thing that would have changed up here would be what? If I said red and then blue instead of red and then green. Well, let's try it. I got a few people looking at me like I'm crazy. Probably red and then blue. Well, probably the first one's a red one is still 4 out of 14. Then you drop it back in. That's probably the next one's a blue one. 3 out of 14. And then whatever the shit that is, it'll be 2 out of 7. So it'll be 6 out of 98. Oh yeah, I could have done that one too. Yeah, just a bit over 6%. Right? Okay. All right, let me stop there. The numbers are not nearly as important right now as the understanding how to do the problem. Right? You can do whatever you want to with the numbers. Who cares? So you understand how to set the problem up. Now, just before I leave this with replacement idea, what if I picked 3 with replacement? Do you understand how it would just be the same thing? You just tack on one more link. What if I want the probability I get a blue and then a blue and then a red? Yeah, so it'd be blue would be 3 out of 14. You put it back in, so then the next one being blue is still 3 out of 14, and then you put that back in. What's probably the last one's a red one. 4 out of 14. And then whatever the hell that is. Right? Almost don't care. Okay. So I mean, I can make this long ass chain of stuff. Okay. So what happens if I do this without replacement? Let's see if I can do this. I'll keep this up here somehow. So if I do this without replacement, if I do like this one without replacement, probability red and then green. Well, the first one, I haven't picked anything out yet, so it's probably the red chip. 4 out of, red, sorry. 4 out of 14. And then I feed that to my little brother. Why has trouble with percentage now? Exactly. Now, how many green are still in there? All 7. But how many chips are in there? 13. And real quick, what is that the probability of green? 7 out of 13. Is that the probability of green? No. What's the probability of green? 7 out of 14. Right? What is this then? This is the probability of green given that I picked a red one. So RG is the probability of red times the probability of green given that I picked a red one already. Which, if you look back, is the formula for AND that we got earlier. That's why there's a given in it. Why would there be a given? Because if it's not independent, the probability is going to change. This depends on what you picked first. The next probability is going to change. That's why there's a given in the formula for AND. It's still basically multiplication. Just like OR is basically addition. There's just a little adjustment in case the next probability and the next one and the next one depends on what just happened. There's that little adjustment in the formula. So much, Jeff, I know. Okay. So what would, let's do that BBR again. Probability of BBR. If I pick 3 without replacement, without putting them back in. What's the first one is a blue. What's the probability that's true? I erased all the numbers. What was it again? 3 blue,
4 red, 3 blue, 7
4 red, 7 green. Okay. Probably first one's a blue. 3 out of 14. Then I throw that one away. So my little brother got smart. I'll stay away from it. So now, good. There's one less chip, but there's also one less blue. But now what about that last red? Yeah, still all 4 red. Why? Because I haven't picked a red yet. So still all 4 red options there, but now there's only 12 chips left in the back. Okay, cool. I like it. Some of you guys are like, what the hell is this? It's really not that bad. I know you just learned it today, so let it sink in. Some of you guys realize how it's not nearly that evil. So that'd be 1/3. 3 goes into 3. 2 goes into 14. 1, 7. 7 times 13 is 91. No one had a 91, which is rough, whatever. 1.7%. Well, some of you guys, I got a calculator to do all this shit as well. Okay, I like it. So one last idea, and then I'm going to finally stop talking and let you guys work on something here in class. And that is the idea of what do you do when we're talking about a huge population? There's something I can assume, thank God. Because anybody know how many Americans there currently are? I actually have lost track. I haven't looked in a few years. Yeah, I think in October 2008 we passed 300 million. That's the last time I really paid attention. Let's just pretend like we're up to 350 million. We got what they want here? Is that still going? Yeah? Okay. It's a troop. It's going to take a union break here in a second. So let's say the probability of an American being left-handed is 11%, which is roughly the current estimate. How many got anybody in here left-handed?
Me.
1, 2, 3, 4. Out of roughly 50. It's about 8%. It's probably a little less than 50 in here, I think. So, yeah, okay. So that's close. Okay. So hopefully you understand. The fact that 11% of all Americans are left-handed means that a good guess for any subgroup of Americans would be 11% of the total. Does it have to be exactly that? No, that's what I expect on average. But of course, every group is going to be composed differently. If I had like 30% left-handers in the class, I'd go, what happened? So it should be close to this, but doesn't have to be exactly equal to that. So, where do I go with this? Forgot where I want to go. Oh, yeah. So let's say I pick 4 Americans. I want to know the probability that Now, when I say pick 4 Americans, do I mean that they could be the same person? Pick 4 Americans, I actually mean 4 different people, right? But there's an assumption I can make, because if I want to know probably that the first one is left-handed, well, the last 3 are not. Let's just say it like this. Because not left-handed doesn't have to mean that you're... What was it last semester? Somebody said, what if somebody lost both their hands? You know, oh, shit, I'm sorry. Never meant to be insensitive. So left-handed, not left-handed. All right, that carries every other possibility. You with me? I don't know if you guys ever saw the guy in the Balboa Park that played the guitar with his feet. Did you guys ever see? Mm-hmm. Yeah, played the guitar better than I think I ever will. With my hands, he played it with his feet better. Anyway. So, my God, please, dear God, you do not have to do out of 350 million, what's 11% of 350 million? Put that down there, and then put 349,999,999. The rule is, if the sample you're picking is less than 5% of the population, then you can just assume that this stays the same. What is 11% of 350 million? It's like 3.8 million something. What is it exactly? Who's got that? You can just do 0.11 times 350 and then tell me million at the end of that number.
38.5 million.
Say again? 38.5 million. I like it. So 38,500,000. All right. So 38.5 million out of 350 million, right? Let me write it all out. That's 11%. Stay with me. This is a little boring, but I want to really show you the math. If I take one person, one left-hander, now I've got 38,499,999 out of 349,999. Now, what is that if you divide it? Somebody help me out. You got calculators. You guys see what happened? If I take one left-handed person and put them in a different country for a minute, now there's this many left-handers out of this many people. When you divide this, what do you get? Which is basically 11%, right? 0.10999999. Of course it is. It's going to barely change. I mean, so when the sample I'm picking is less than 5% of the population. And what's 5% of 350 million? More than 4. Then I could just do this. This is awesome. What's probably the first one is a left-handed person? 11%. What's probably the next one's not left-handed? 89? 89? 89. If the sample I'm picking is less than 5% of the population, I don't have to worry about the denominators changing and all that kind of bullshit. I just put the percentages. In fact, there's a better way to write this. 0.11 times 0.89 to the... Why does this make sense? I got 1 left-handed person and 3 not. You can actually see it in the math. You can read it as a sentence. And then whatever the hell that is. I don't know. 9.81.72.08? I don't know. Somebody save me from myself. No? 0.077.
0.7.
Sorry. It's my one skill, so I got to show off every now and again. All right. Somebody's like, he did that before class. No. Okay. So what I want you guys to do. This is very, very clearly marked. There's a side that says this side in class. And there's a side that says practice for the quiz. So the practice side, I'll have an answer key for Wednesday. Side in class, you should do now. Okay. You can work together. when we do this kind of thing, I want you to understand you can totally have your notes out, you can help other people. I mean, that's the point, is just to try to fully make sense of this from what I said, from examples. Unfortunately for you, if you don't have a calculator, I didn't bring them with me. Just at least set up the fractions related to the answer, because that's actually what's more important.